This is 4.3 logarithmic functions. A logarithm means for y equals a to the x, the log base a of y equals x. So that's the base. What's inside the log is called the argument. You guys already know what an exponent is. Okay, so the log scale tells you what number or how many times do you need to multiply the base together to get the argument. So, for example, if we wanted to give the value for log base 2 of 32. This means we are multiplying 2 together a certain number of times until we get 32. So 2 times 2 times 2 times 2 times 2 equals 32, which is 2 to the 5th. So log base 2 of 32 is 5. Equivalently, we can say 32 equals 2 to the 5th. These statements in their entirety give us the same information. This statement says if we multiply 2 together 5 times, we get to 32, or the log base 2 of 32 is 5. This is something you're more familiar with. 32 is 2 to the 5th power. So if we were to write as an exponential equation, let's say log base t of b equals c. That logarithm is the same thing as saying b equals t to the c. Okay. So a logarithmic function is log base a of x. Now, the log function, I'll mention this now, is the inverse of the exponential function. So a is the base of the exponential, it's the base of the logarithm. When we talked about exponential functions, a couldn't be 0 and it couldn't be 1 for obvious reasons. So same thing goes for the log base. A is strictly greater than 0, it can't equal 1, and the independent variable is a positive number, so x is positive. So the domain of the logarithm is the range of the exponential function, which is 0 to infinity. So the domain of the log function is 0 to infinity, not including 0. The range is all real numbers. There is a VA at x equals 0, and we have an x-intercept at 1, 0. So f of x, if f of x is a to the x, f inverse is log base a to the x. And if you remember from 4.1, inverse functions swap domains and range. It requires, for a function to have an inverse, a function has to be 1 to 1. And if it is 1 to 1, then when we swap their domain and range, we get the inverse. So the inverse of the exponential is the logarithm and vice versa. So we can graph log functions a couple different ways. We can use graph translations. We did some translations a little bit in exponential functions. We can do the same thing. We can take a log curve and we can move it up, down, left, right, flip it over an axis, you know, that type of thing. So we can keep coming back to just, you know, shifting that around. We can always just plot the ordered pairs. So, you know, if we had the log function here, log base 2 of x, we could plot these ordered pairs, and then we know that, you know, this logarithmic curve is going to be similar to an exponential curve, except you have the x's and y values swapped. So you're going to have the same curve, but reflected across the diagonal y equals x. And then that's another common way to graph logarithms, is to graph the inverse, which is the exponential, then reflect across y equals x. So here is the exponential function 2 to the x minus 1. Now if you remember correctly, x minus 1, so if we subtract 1 from the independent variable, that shifts the graph to the right. And so then if we I think I want to do plus 1 there. Yeah, this needs to be plus 1. Sorry about that. Then this would be plus 1. Just need to finish it off. Okay. Then if we did that, if we reflected it across the diagonal after we graphed 2 to the x plus 1, we would have this logarithm. So there's a VA here at x equals 0. We're going to have an x-intercept at 2, and we could plot those points along the way. So if you did graphing using the inverse, if you picked an x value over here on 2 to the x plus 1, that would be the y value over here. Logarithms have properties that at first may not seem super awesome, but they are extremely useful and would make life much more difficult if they didn't exist. So the product rule, if we have multiplication inside a single log, we can split the log into 2 using subtraction. So we would have log base a of x plus log base a of y. The quotient rule is very similar. If we have log base a of x over y, then we can split that into 2 logs with subtraction in between the two. The bases stay the same. The power rule is very powerful. We have an exponent. That exponent can come out front and become the leading coefficient. This right here isn't necessarily a property, but we need to know that log base a of 1 equals 0, so it doesn't have a name. When I say it's not a property, I mean it doesn't have a fancy name like this. Let's do the log to exponential transformation, and we can clearly see, because we're probably pretty comfortable with exponents, that this is a true statement. So if log base a of 1 equals 0 is the same thing as saying 1 equals a to the 0. So anything, any non-zero to the 0 power is 1. So let's do the same thing with log base a of a equals a to the first. So if we did that transformation again, we'd have a equals a to the first, which is a true statement. So this statement is something we've known for a long time. A is equal to a. So this logarithm, log base a of a equals 1, is another way to write that. Now, this equation, or this equality, comes from the fact that log and exponential are inverses. So if you go back to 4.1, inverses, when you compose them, you get the original independent variable. So in this case, we generally just use x. So if I have log base a of a to the x, so that is a composition with the exponential inside the log, that simplifies to just x. Now, we can show this using the power rule combined with this property, that log base a of a is equal to 1, and we get just x. Okay, so that's using some new properties that we just talked about. And then remember that inverse functions, the reverse has to be true. If you compose the inverse inside of the original function f, then it also has to equal x. So when we have the exponent of the base a is log base a of x, since a to the x and log base a of x are inverses, that also simplifies to x. Okay, so a couple examples where we're just practicing the properties of logarithms. Rewrite as a single log with coefficient 1. So what we would do is we would use the power rule, and we would put the 2, that's the coefficient out front, we would put that as the exponent, and then we do that same thing over here, and we'd have log base 3 of t to the 7th. Then we're set up for the quotient rule, so if we have two logarithms with the same base separated by subtraction, we can write that as a single log with division. So if we wrote that as a single log with coefficient 1, it would be log base 3, x squared over t to the 7th is the argument of that logarithm. This example is the exact opposite. So we're going to expand the logarithm and simplify it as much as possible. So we are doing the previous problem, but in reverse. So we have division inside the log, so we would split that up as 2 logs with subtraction. Okay, now on this first log base 4 of 16 times x, that has multiplication, so we can use the product rule. So we have log base 4 of 16 plus log base 4 of x, and then log base 4 of t squared, we can use the power rule and bring the t out front, bring the 2 out front. Now there's one more thing that we can do. Log base 4 of 16 simplifies to 2. So log base 4 of 16, if we're just looking at this, log base 4 of 16 says, how many times do I multiply 4 to itself to get 16? That answer is 2, because 4 times 4 is 16. So that would be 2. And this is as simplified as we can get for that. A 4.3 has a decent amount of problems like that, and just a little bit of graphing. So enjoy.